We can now see your email also.
Oh, right. I forgot. Yeah. Okay. Let me. Right.
Hello.
Yeah. Hi.
Good morning, sir.
Good morning. So let me know when it's time to start.
Sir, it is just 1 minute.
Sure.
Hello, Dr. Krishnanji. हेलो
हाँ गौरव शंकर जी बताइए.
गुड मॉर्निंग. तो स्टार्ट करें हम?
Maybe wait for 2 minutes and then start.
Yeah, sure. Whenever you are ready, let me know.
Yeah. आप तो शुरू कर दीजिए गौरव शंकर जी, वो होते होते तो 2 मिनट हो ही जाएगा.
अच्छा, ठीक है. So, good morning to all of you. So, firstly, I welcome you all in the morning session of the 16th day of NASI TMC Summer School and Differential Geometry. So, today's speaker is Professor Harish Seshadri ji from IIT Bangalore. He is a well-known and admired differential geometer across the world. He joined IIT Bangalore as an assistant professor in 2004. And as far as his education is concerned, he has completed his integrated master's degree in mathematics from IIT Kanpur in 1994, and after that he did MS from Johns Hopkins University in 1995. And then he completed his PhD from Stony Brook University, USA in 2001. And Professor Seshadri has been visiting faculty in several US universities, including University of Oregon during 2001-2. And after that, he has been research associate at ISI Bangalore from 2002 to 2004. His research interests lie in geometry of intrinsic matrix in complex analysis, curvature of Kähler manifolds, Einstein manifolds, conformal geometric invariants arising in Riemannian geometry. And so far he has more than 45 publications in reputed national and international journals. His publications are just some journals like Proceedings of American Mathematical Society, Transactions of American Mathematical Society, Differential Geometry and Applications, Journal of European Mathematical Society, etc. And he has also published several surveys articles and expository articles in different reputed journals. So with this brief introduction, I would like to invite our distinguished speaker, Professor Harish Seshadri ji, for his talk on volume and diameter of positively curved Kähler manifolds. So over to you, sir.
Okay, thank you, Gauri Shankar and Krishnendu, for the for your kind of invitation to speak at this conference. So all of you, the participants, must be quite exhausted after 3 weeks almost of this workshop. So I'll try to keep it light without, in any case, it will be very hard to go into technical details. So, but I hope I'll be able to convey some flavor of this work that I was involved in. I'm still involved in.
Sir,
Now,
Professor Kulkarni sir has also joined. Good morning, sir.
Who?
Professor Ravi Kulkarni.
Okay. Yeah, right. So let me, okay, so let me begin. The theme of this talk will become clear. So as my title says, I want to talk about geometric quantities, namely two specific quantities, the volume and diameter of Kähler manifolds with positive. Deliberately, I've kept the title somewhat vague. Positively curved could mean many things. But I'll be dealing with only two notions of positivity. And in fact, the Riemannian results I'll be talking about just involve one notion of positivity, namely positive Ricci curvature. So let me begin. So I want to, the first part of the talk, I'll be talking about what are called comparison theorems in Riemannian geometry. This is a huge subject which has seen some very dramatic advances in the last decade or so. But the early results date back all the way back to 1930s and 1940s. So the general theme of comparison theorems in Riemannian geometry is you want to make. So the idea is that the more positively curved a space is, the smaller it should be. Of course, the key thing to understand here, what exactly does smaller mean and what does positive curvature mean exactly and so on. But this is the sort of background behind comparison theorems. One wants to make this idea precise. So let us recall some early results. Now, when we want to say smaller, obviously we need to have some space, a standard space. With reference to that, it should be smaller or bigger. Now, in the case of, in the context of positive curvature, the model space is the standard round sphere of radius 1. Well, actually, radius 1 is not important. It can be any radius, depending on what our curvature bound for our given spaces. But let's take the round sphere of radius 1. This has the property that the Ricci tensor is n-1 times. Of course, here when I say standard round sphere of dimension n, and this for that the Ricci curvature is n-1 times the metric. Ricci tensor is n-1 times the metric, and the diameter, of course, as we know, is pi. So here comes the first theorem in this in this area, the Myers-Bonnet theorem. So the theorem states that if you have a complete Riemannian n-manifold, now you say Ricci curvature greater than or equal to n-1 times the metric. For the sphere it was equal, but here you demand that it's greater than or equal to n-1 times the metric. Then So if you plug in a unit vector, if you evaluate Ricci of x comma x, then you'll get greater than or equal to n minus 1. So in other words, the curvature is more than that of the sphere. Here, if Ricci of x comma x will be actually equal to n minus 1, then the point is that this will force the diameter of the manifold to be less than that of the sphere, in particular hemisphere. So this is something we all learn in any first course in Riemannian geometry. But this is a significant first step in the notion of in this plan to obtain comparison theorems. So the more, since I assumed it's compact, and here we are saying it has to be bounded. So since I've assumed complete and I've said the thing is bounded, so it is compact. Now, apparently, the German mathematician Bonnet had proved this for surfaces way back in 1850s. The significant contribution of Myers, almost a century later, was that he realized that for higher dimensional generalizations, you don't need the full sectional curvature, just Ricci curvature is enough. And that's what we have here. And proof, if you have seen it, you might recall that this is just a straightforward application of the second variation formula for the length functional on the space of curves. So you take a minimizing geodesic which realizes the diameter and then use the second variation formula. And you try to construct variations. Basically, you want to say that if diameter is more than pi, then you should be able to come up with a variation of that curve which will force the second variation to be negative actually, which would be a contradiction, since we started with a minimizing geodesic. The second variation should be positive for every variation of the given geodesic. Now, already at this stage, it becomes so. Here we have this greater than or equal to and less than or equal to. So the natural question to ask in these types of things is what happens if the diameter is actually equal to pi? Ideally, we should expect it to be isometric, the given m to be isometric to Sm. It is true, but it is not so straightforward. It doesn't follow from the proof of this theorem. So the equality case does not follow from the proof by Myers-Bonnet. And this was much later on, almost 30 years later. This was proved, the equality case was dealt with by Cheng. This is Cheng's maximal diameter theorem dating back to 1975. Let Mg be a complete Riemannian manifold. Well, even though I've said complete, I mean, we already know it's compact actually. So let M be a compact Riemannian in manifold with the same Ricci bound, and if the diameter is pi, then M is isometric to Sm. So this requires a different set of ideas. The second variation formula will not do for this. So Cheng actually used information about eigenvalues of the Laplacian of such manifolds. And then using that, he was able to get this. There are other proofs of this as well. Now, coming to volume, right. So now I'll start the same hypothesis. You start with a compact Riemannian in manifold with Ricci curvature greater than this, whatever it is for the sphere, n sphere. then again, the volume, since we expect the manifold to be smaller, the volume is less than that of the sphere. And if equality holds, then M is isometric to Sn. So this was proved by Bishop in 1963. Here the equality case is not that difficult to handle. It follows from the proof directly. But this Bishop's theorem has had a tremendous impact on differential geometry, differential geometry and metric geometry in general, not just positive Ricci curvature. One can replace this with Ricci, just any lower bound on Ricci curvature. Then one will be able to, it can, this right hand side can even be negative here. And then one will still get volume upper bounds. And this has been studied extensively by, so Gromov later generalized this theorem, which has far wider implications. But that's not, Gromov's generalization is not so relevant for this talk. So I'll just mention Bishop's theorem here. Now, this was way back in 1963. Then we jump almost 30 years later when Tobias Golding, so various people were studying by then, during those 30 years, the Gromov had a tremendous impact on Riemannian geometry in general. In particular, the notion of Gromov-Hausdorff distance between two Riemannian manifolds had begun to play a prominent role. And so, in this context, Golding proved an almost rigidity version, almost rigidity result, which generalizes the equality case in Bishop's theorem. So what do I mean? Well, the equality case is that if volume is equal to the volume of the sphere, then M is isometric to Sn. What if under the same Ricci lower bound, the volume is close to that of the sphere? It may be less, it has to be less, but it doesn't differ from the volume of the sphere by too much. It's lesser by only a small constant. Then what can we say about the manifold? So we would expect that if the volumes are equal, then they're actually isometric. So if volume is only slightly less, one would expect that the geometry of M should be somewhat similar to that of the round sphere. Now, the somewhat similar is the heart of the matter. That's where the notion of Gromov-Hausdorff distance comes in. So that's what I'll talk about. So you want to basically compare two metric spaces. If they're isometric, we want to say that their distance is 0. They're practically the same space. But if the distances between the two metric spaces is small, then one has a sort of precise notion of the metrics being similar while not literally being isometric. So here's how one would define the Gromov-Hausdorff distance. Let x dx, y dy be compact metric spaces. A map, which need not even be continuous, it's just a map from x to y, is said to be an epsilon approximation if the distance between f of x1 and f of x2 in y minus distance between x1 and x2 is modulus of this is less than epsilon for all x1 and x2. Of course, if f is an isometry, then this difference is actually equal to 0. But here we just demand that this is less than epsilon. And to say that f is almost surjective onto, we would like, we don't want to embed x inside y. And that's not good enough. We want to say they're of the same size, more or less, same size and geometry. So to that end, we don't really care if it's actually onto or not. But what we need is the image of x, f of x inside y. If every point in y should be epsilon distance from the image. So it almost occupies the whole of y. That's the idea. So the epsilon neighborhood of f of x is equal to y. This is an epsilon approximation. Now, the Gromov-Hausdorff distance between x and y is defined to be the infimum of all such epsilons, such that there exists, but we want it in both directions. There exist epsilon approximations f from x to y and g from y to x. One can check that, of course, if x and y are isometric, then it's clear that the Gromov-Hausdorff distance is 0, but the converse is also true if one is working with compact metric spaces, that if the Gromov-Hausdorff distance is 0, then x and y are isometric. So this perfectly captures, this notion of distance captures when two metric spaces are sort of similar to each other, at least in terms of their distance functions. Now, when we come to Riemannian manifolds instead of metric spaces, then the obvious thing to do is we define the Gromov-Hausdorff distance between Riemannian manifolds to be the Gromov-Hausdorff distance between the corresponding metric space structures. The Riemannian metrics will induce distance functions on both manifolds, and we forget the Riemannian metric, but just look at the metric space structures. So with this notion of distance between manifolds, Golding proved in 1996 the following generalization of, so let's recall this Bishop's theorem, that if volume is equal to that of Sn, then M is isometric to Sn. Under this, the key point is this Ricci curvature bound. So we would like to retain this curvature bound and then say that if volume is only slightly smaller than that of Sn, then M is, as a metric space, is close to that, the round sphere. And that's exactly what he proves. Given an epsilon greater than 0, there exists delta such that if you have a compact manifold with Ricci curvature greater than this, and the volume of M is greater than volume of Sn minus delta. Of course, on the volume of M has to be less than or equal to volume of Sn by Bishop's theorem. But here we demand that it's greater than this. Then the Gromov-Hausdorff distance between M and Sn is less than epsilon. So this theorem of Golding it's quite non-trivial. It requires far more work than Bishop's original theorem. And in fact, Golding not only, he also proved, so around the same time, Golding also proved the converse. The converse would be that if the Gromov-Hausdorff distance is less than epsilon, then the volume of M should be close to that of Sn. Now, if you, to get an intuitive feeling for all this, one must realize that this notion of Gromov-Hausdorff distance is a very crude one. Like I said, you don't even have continuity. if you start with an epsilon approximating map, this F need not even be continuous. So it is just in a very rough sense, it's capturing things. So local information is lost in some sense. But still, surprisingly, under this key hypothesis of Ritchie-Curvature bound, volume is the notion of Gromov-Hausdorff of closeness to the sphere at least. Volume is completely determines when two things are close. So both of these statements are not obvious. That if the volume is closed, then Gromov-Hausdorff distance is closed is also not clear. Volume being closed is an extremely weak notion. And even though Gromov-Hausdorff distance is also weak, it's certainly in general this contains much more information than just volume. And the other direction also is not clear, that if Gromov-Hausdorff distance is close, then that the volume should behave like this. Now, short time after that, in fact, Kähler and Golding proved that under the same hypothesis meaning this one, that Ritchie curvature is of M is greater than is equal to n minus 1, and Gromov-Hausdorff distance is small. Oh, here I've written, this should be corrected. This just repeated this here. The implies in the above statement, it should be volume. The volume statement should be made. Volume of M greater than volume of Sn minus epsilon should be here, not this. So, if the Gromov-Hausdorff distance is small between M and Sn, then M is actually diffeomorphic to Sn. And this actually, under the same hypothesis, the fact that M is homeomorphic to Sn was proved by Perelman in 1994, and Kähler and Golding improved it to diffeomorphic to Sn. So the results in the Riemannian case, all we needed for both the diameter results and the volume theorems, one was working with just positive Ritchie curvature. But surprisingly, it turns out that the analog of the Myers-Bonnet diameter theorem under a positive Ritchie curvature bound is not true in the Kähler setting. For Kähler manifolds, of course. So when I say analog, in the Riemannian case, we compared the diameter with that of the sphere. In the Kähler case, the spheres are not complex manifolds, as we know, other than n equals 2. At least, they're certainly not Kähler manifolds for n bigger than or equal to 3. The sphere is not the model space anymore. It turns out that the model's positively curved space in the Kähler setting is a complex projective space, CPN, endowed with, this comes with a natural metric, the Fubini's 2D metric, GFS, of constant holomorphic sectional curvature. Here I've taken the normalization to be 2. This exact value is not important, but it's a Fubini's 2D metric up to some multiple. Now, this holomorphic section, I said homomorphic, it should be holomorphic. Holomorphic, what does, this holomorphic sectional curvature just means, just refers to the usual sectional curvature, but instead of considering sectional curvature of all two-dimensional subspaces of tangent spaces, you just look at two-dimensional subspaces which are invariant under the J operator, the almost complex structure. So another way of saying it is to look at complex lines inside. The real dimension of CPN is 2n. So the tangent space will be R2n. But inside R2n, if you identify R2n with Cn, then there are certain distinguished two-dimensional subspaces, those coming from complex lines. And you just evaluate sectional curvature along those two-dimensional subspaces, and that we demand should be the same constant at every point on the manifold. So why is this the model space? Why is this so special? Well, it turns out that it's exactly analogous to the Riemannian setting. In the Riemannian setting, one knows that sectional curvature determines the full curvature tensor. And moreover, a space with constant sectional curvature, see, if you take a constant positive sectional curvature, then such a space is actually, if you assume, is locally isometric to this round sphere. The same thing happens here. The holomorphic sectional curvature of a Kähler metric determines the full sectional curvature, curvature tensor. And if the holomorphic sectional curvature is a constant, positive constant, then the manifold is locally isometric to complex projective space endowed with a multiple of the Fubini's 2D metric. So this plays the same role as sphere in Riemannian geometry. So we want to compare volume and diameter under appropriate curvature bounds with the volume and diameter of CPN. Now, for this Fubini's 2D metric, it turns out that with this normalization, constant holomorphic section curvature 2, the Ricci tensor will be n plus 1 times the metric. So remember that CPN, the real dimension is 2n. So here n refers to complex dimension. So real dimension is 2n, but here what occurs here is n plus 1. And the diameter turns out to be pi over square root of 2. So the reason why I mentioned this is, in our comparison theorem, whatever we want to state, we would like to ideally say that, for example, for diameter, that if Ricci curvature greater than or equal to n plus 1 GFS, then diameter of M should be less than or equal to pi over square root of 2. Similarly, for volume, if Ricci curvature greater than this, if we start with the Kähler manifold as Ricci curvature is greater than this, then the volume should be less than, I have not stated the numerical value of the volume of CPN, which is also quite simple, but anyway, that's not relevant. For that matter, even this explicit number is not so relevant since I'm not going to go into details. But the problem is that the diameter, expected diameter bound is not true. It doesn't hold. So in fact, a simple example is you take the n-fold product of CP1s. This one should be in the exponent. CP1 is just the one-dimensional complex projective space is just the real two-dimensional sphere. And the Fubini-Vistudi metric just turns out to be just the round metric. So right. CP1 times CP1 with the product metric. The product metric is the round metric. Each CP1, you take the round metric, but of curvature. So you take the round metric, yeah, and then you multiply that by 1 by n plus 1. Then it turns out that the Ricci tensor is equal to this normalization which I had holds. That's the point of multiplying by this. But the main thing is that the diameter now, you can easily calculate using Pythagoras theorem that the diameter will be square root of n over n plus 1 pi, which will be more than pi over square root of 2 if n is greater than or equal to 2. So the upshot is that this manifold satisfies the required Ricci lower bound, but the diameter is not less than that of complex projective space. It becomes more. So this was it's not entirely clear why this, I mean, there's no intuitive reason why this fails here. At least I can't see this, but it turns out that the correct diameter bound holds under a stronger notion of positivity of curvature. This notion of positivity exists only in the Kähler setting. This, what I'm about to speak about doesn't make sense in the Riemannian setting. But this is actually a very important notion in Kähler geometry. This is the notion of holomorphic bisectional curvature. It's something like sectional curvature, but slightly weaker. So we say that M has positive holomorphic bisectional curvature bounded below by K if Rxy plus Rxjy. See, one has this J is the almost complex structure, which is J squared equal to minus identity, which this comes along with, this is there for every complex manifold. You don't need a Kähler metric. This is coming from the complex structure, but the point is Rxy is sort of like the sectional curvature, but except for a factor, normalizing factor. Like, similarly, it's like sum of two sectional curvatures, and that you demand greater than K times, this is again a normalizing constant to make the whole thing scale invariant. So this you want, yeah, right. So you want this to hold if M is bounded below by K, if this is true. So in any case, the point is that if M actually has positive sectional curvature in the Riemannian sense, then both of these terms will be positive, and so the sum will also be positive. One can check that this constant is also fine. So this positive holomorphic bisectional curvature is implied by positive sectional curvature. But since we are dealing with the sum of two things here, we can't say both either. One of them will be positive, but we can't say both are positive. So it doesn't go in the other direction. But it does imply, it's not difficult to check. And we denote this condition by B greater than or equal to, say, B standing for bisectional curvature. This condition implies positive Ricci curvature. So in fact, if we have this B greater than or equal to K, we'll get Ricci greater than or equal to K times n plus 1 G. Right. So with this bound, at first sight, this appears somewhat unnatural that why one should consider this specific combination of sectional curvatures. But as it turns out, this has proved to be this was introduced by Bishop and Goldberg way back in the 1960s, and it has proved to be a very important notion in Kähler geometry. And various important things, various theorems can be proved with this notion of actually, even the negative condition here is also very useful. So let M be a compact Kähler manifold with B greater than or equal to 1. Then the diameter is less than or equal to that of CPN. This was proved by Tam and Yu in 2005. And unlike Bishop's original proof, not Bishop, Myers-Bonnet original proof of diameter comparison, this doesn't come from second variation of arc length, but instead one uses a comparison theorem for Laplacian of distance functions. Using that, one can get this. And the same proof can also be used to recover. It also gives a different proof of Myers-Bonnet for Riemannian manifolds. The second variation proof of Myers-Bonnet is much shorter, but that works only in the Riemannian case. But interestingly enough, so this basic result was proved only in 2005, but the equality case here is still unknown. Even though bisectional curvature was introduced way back in the 60s, let M be a compact Kähler manifold with, if diameter M equal to diameter of CPN, does it follow that M is isometric to CPN? Again, the equality case cannot be handled by this, the proof of this inequality case here. So this question as of now is still open. Even more surprisingly, the analog of Bishop's theorem about volume was proved only 2 years ago. Zhang proved that if M is, here we no longer need to work with bisectional. Ricci curvature is good enough for Zhang's theorem. Let M be a compact Kähler manifold with Ricci greater than or equal to n plus 1 G. Then volume of M is less than or equal to the volume of complex projective space. And if equality holds, then M is holomorphically isometric to complex projective space. Now, this fundamental theorem, it looks very similar to the Riemannian case, except that you replace CPN with SN. But the proof is highly non-trivial. And in fact, our original interest was to give a simple differential geometric proof. This proof uses considerable bit of algebraic geometry and lots of other non-trivial things relating to some recent work in Kähler geometry. So it uses very heavy machinery to prove this simple-minded result, simple-looking result. It would be of definitely of some interest to give a proof which only involves differential geometry, but so far that has been lacking. Now, right, and so the equality case can also be dealt with. The same proof will also give the equality case. So if equality holds, then M is isometric to CPN, but in fact you can choose the isometry to be biholomorphism as well. So both the complex structure and the metric structure are the same with that of CPN. Now, right, once we have, so now I'll focus the rest of the talk, I'll just talk about this only volume. The diameter will not play a role. So regarding volume, recall that we had Kolding's theorem in the Riemannian setting that a volume is close to that of the sphere, then the Gromov-Hausdorff distance is close between M and the sphere are close. And Kähler-Kolding also said that M is actually diffeomorphic to the sphere. So in the paper of Zhang, Liu in an appendix proved a holomorphic analog of the Kähler-Kolding diffeomorphism stability theorem. So the statement would be that there exists epsilon greater than 0 such that if Mn is a compact manifold, Kähler manifold with Ricci greater than this, whatever it's for the Fubini's 2D metric, and the volume is greater than volume of CPN minus epsilon. So we already have the upper bound from Zhang's theorem. So now we want a lower bound. If this holds, then M is biholomorphic to CPN. So this is the direct analog of the Kähler-Kolding diffeomorphism theorem. But what was missing was Kolding's theorem that, so this says that the complex analytically, if these two conditions, if the volume is close, then complex analytically it's the same as projective space. But what was missing was, what about the metric structure? If the volume is close to that of the CPN, does it follow that the Gromov-Hausdorff distance is also small? And that is what we proved. This is joint work with my colleague Ved and his advisor Song. Subsequently, the analog of Kolding's Gromov-Hausdorff closeness theorem was proved. Given epsilon greater than 0, there exists delta such that Mn is a compact Kähler manifold with Ricci curvature greater than this, and volume is again the same hypothesis as before. But now we say that metrically the manifold resembles CPN. So this is the Kähler version of Kolding's theorem about Gromov-Hausdorff closeness. That completes the statement of results. Now, the proof of this, again, even though the proof is short, it is short because it involves some highly non-trivial results arising. So recently meaning in the around since 2013, there was a substantial breakthrough in Kähler geometry due to Tian and Chen, Donaldson and Sun regarding Kähler-Einstein metrics and stability, the algebraic geometric notion of stability. So a substantial body of work was developed around this. And this uses, this theorem uses various things from those works. So the proof is, it's somewhat unsatisfactory because it, one has to use highly non-trivial results from which are a priori not related to this. So it would be interesting to prove both Zhang's theorem and this Gromov-Hausdorff closeness theorem in a more direct differential geometric way. But such a thing is, as of now, there's no approach without going into algebraic geometry. So I won't be able to give any details, but let me just state the main technical result, which is which will give what we want. Everything will be hidden in this, the proof of the technical result. So for the rest of the talk, I'll assume, now let me change the normalization. Instead of Ricci, I said that the Fubini-Studi metric is normalized so that Ricci is equal to n+1 G. But I'll rescale it so that Ricci equal to just G itself for the Fubini-Studi metric. I'll assume that the Fubini-Studi metric on CPN is normalized so that Ricci equal to the metric itself. So the main lemma which will give the theorem is the following result. So in what follows, omega will denote the Kähler form of a Kähler metric. We know that whenever we have a Kähler metric, we can get an associated complex form, differential form of type 1,1, which is closed. That's omega. So let M, here now I'll assume that let Mn GKE be a Kähler-Einstein manifold with Ricci curvature equal to GKE. So the normalization, Kähler-Einstein just means that it's Einstein. The Ricci tensor is a multiple of the metric tensor, and the metric is scalar. So I'll rescale so that Ricci is equal to GKE, the same as the Fubini-Studi metric. Suppose that we have a sequence of numbers, positive numbers delta I going to 0, and Gi is a sequence of Kähler metrics on M such that omega I, each of these omega i's, the Kähler form, 1 Kähler forms, they're closed forms. So they give rise to cohomology classes in the second cohomology group of M. Now there's a distinguished cohomology class, second de Rham cohomology class on M, namely the first Chern class of M. So we demand that the Kähler forms of this sequence all belong to the first Chern class of M. And Ricci Gi is greater than or equal to 1 minus delta I Gi. Then MGI goes to converges in the Gromov-Hausdorff sense to the Kähler-Einstein metric. Now, what does this have to do with what we set out? Where did volume disappear? Well, all that has happened here is if you can normalize, suppose you start with, yes? Let's say we start with this. So as usual, the proof is by contradiction. Suppose that this theorem fails, then we would get a sequence so that the volume gets closer and closer to that of CPN, but the Gromov-Hausdorff distance stays bounded away from zero by a fixed constant. So that is the starting point. But what one does is, this volume greater than this, if you normalize so that the volume is actually equal to this, volume of M equal to volume of CPN, then this Ricci curvature bound will get changed. So that is what is happening here. Instead of you just normalize, well, this theorem doesn't use that, but that's how it's going to be used. When you normalize so that the volume is equal, then the Ricci curvature, it gets translated to a Ricci curvature bound like this. Now, what about the first condition? This is a non-trivial condition that omega I belongs to C1 of M. This is not by the way, another thing I should mention is when I assume that this theorem is not true, not only do I get a sequence of metrics, the manifolds themselves will change. So you'll get a sequence of manifolds and sequence of Kähler metrics on those. See, you get a sequence of compact Kähler manifolds, in short, not just a single manifold with a sequence of metrics. But that's okay. So the point is that, this omega I belong to C1 of M, this condition is not, is a non-trivial condition, but here's the point. By Liu's result, the volume closeness, if you start with this hypothesis, the fact that volume is closed, Liu's result tells us that M is biholomorphic to CPN. So the sequence of manifolds, all of them are biholomorphic to CPN, so one can as well think of a single manifold. It's just the metrics are changing. And the point is that the second de Rham cohomology group is just one-dimensional. So this condition that omega I belongs to C1 of M is automatic up to scale. It's de Rham cohomology group is one-dimensional, so any two classes are scalar multiples of each other. So this implies that after rescaling, condition 1 of the lemma is satisfied by any Kähler metric on M. If one rescales so that volume of GI equal to volume of CPN, in fact, the rescaling is very specific. You just rescale so that the volume of this metric is the volume of CPN, then this condition holds. One can check that. The point is that the first Chern class of M is given by the this thing, Ricci tensor, Ricci form. So with this normalization, one gets condition 2 as well. Since the rescaling constants will be close to 1, one can see that so basically what will happen is this rescaling constants will be close to 1. So this new rescale matrix GI will be the same as the old ones, more or less. And the original ones will also converge to the scalar Einstein metric. But to finally conclude the implication of the lemma implies the theorem, one just observes that since we already know M is CPN, and one knows that CPN has a unique Kähler Einstein metric, namely the Fubini-Studi metric. So this is just the Fubini-Studi metric actually in our case. And we end up concluding MGI converges to the Fubini-Studi metric, which is a contradiction since we assume that this distance is bounded away from 0. So this considerable bit of technology goes into proving this lemma actually. And so I won't be able to go into that. So let me stop here. So I'm done.
Thank you, sir.
Yeah.
So I invite questions from audience. Please ask.
I have a question.
Yeah.
Yeah. So suppose in your lemma there are two conditions. So if you relax one of them, then what happens? For example, what happens when the Ricci curvature is less than this number?
Oh, if you don't, well, it's not entirely clear. I mean, suppose you relax a condition that omega I belongs to C1 of M, and suppose you just retain this, the second one, then whether this thing holds, I mean, it might very well hold. It's not entirely clear that there is some, for example.
Okay.
But if you drop condition 2 and if you just have condition 1, then there is no chance that something like this will hold.
Okay.
Yeah. The condition 2 is the crucial one. Condition 1 is a more of a technical condition.
Okay. Okay.
Professor M.M. Tripathi want to ask some questions, sir.
Yeah.
Yes. First of all, thank you so much, Professor Seshadri, for such a nice talk.
Yeah, thank you.
I want to know if there are any Sasakian analog for this kind of theorems.
That's something that we briefly thought about, but we didn't pursue it. There should be some Sasakian analogs of these theorems because these conditions, for example, Zhang's theorem that Ricci curvature greater than this, then the volume is less than CPN. Definitely, there should be a Sasakian version of this. But as far as I know, It might be worth having a literature search on this. I vaguely remember somebody using this to get something about Sasakian manifolds, but I'm not 100% sure. But it's a very reasonable question.
Thank you. Thank you, sir.
And I suspect that there should be.
Thank you.
Yeah.
Hello, any other question? Participants, please ask if you have any queries, any doubt. Dr. Prashant Sinha?
No, sir.
No.
I don't have.
So I think there are no questions. Krishnendu, have you any question?
No, I think it's nice. Yeah.
Okay.
I organized several questions, but as you can see, there are several scopes of further questions on this work, and that's very interesting.
Yeah. So if there are no questions, then thank you, sir, for this excellent and inspiring talk on this volume and diameter of Kähler manifold. So on behalf of organizing committee, I am very much thankful to you that you accepted our invitation and shared your thoughts with our participants. So thank you very much, sir. Thank you.
Yeah, thank you. Okay, bye.
Bye-bye.